So basic unit is the cell. So cell is bounded by a membrane, and that's called the cell membrane, or we call it the plasma membrane. So why do you think there should be a membrane? It separates it from the external environment, right? Thus the cell will be protected, and it maintains the balance between the exterior of the cell and the interior of the cell. So it forms the structural and the functional unit of the living beings. Basically, the major component of the cell is the water and electrolytes, which include sodium, potassium, chloride, bicarbonate, etc. And the membrane is made up of three components, that is the proteins, lipids, and the carbohydrates. Okay, I will not bother much about the other part, that is the nucleus and the cytoplasm. So this is how, who proposed this cell membrane? Now see, I ask you all question just to get to know about how much you all know about it, so that I can be either fast or slow. Okay, so it's a lipid bilayer, and it is interspersed with the proteins. Okay, so the thickness of the membrane is around anybody? Am I audible? I don't get any response from you all.
Yeah.
Yeah. Okay. Anybody has an idea what is the thickness of the cell membrane?
Is
Okay,
that 7 to 10 or
10
15?
nanometer. Okay.
Okay.
And the major component of the cell is water. This fluid mosaic model, it was proposed by anybody?
Singer and Nicholson.
Say, very good. Okay. The chief component of the cell membrane is?
It's phospholipids.
Proteins. That
Sorry.
is the proteins. Okay, so you can see here the major component is the protein, that is 55%, and the rest is all less than that. So what is that spans the cell membrane? Well, there are two different types of proteins. The one which will span the cell membrane, which are called the
Intrinsic and extrinsic proteins.
integral proteins, okay, or you can also call it transmembrane proteins. And the one which is on the surface of the membrane, that we call it on the surface, so periphery, which is why it is called the peripheral proteins. Okay, now you have to answer this question. Proteins are enzymes, pumps, ion channels, receptors, and they provide the network. Is this true?
Yeah, true.
It is true. Okay. Now the important component of the cell is the fluid component. So the major component we know now, it is water, which we call it the total body water. Okay. Now, when you have the membrane, then we call the fluid which is inside the membrane. What do you call inside the membrane as?
ICF. The
ICF. What is the full form of ICF?
intracellular fluid.
Yes, very good. Intracellular fluid. That means what is outside the cell, you call it?
ECF.
Extracellular fluid. Okay. So then you tell me, we have the vessels with the plasma and the blood cells. Do you think it comes under ECF or ICF?
It's in the integral. I mean, it's not either in the ECF or the ICF.
No, it is not like that. So the vascular component, we call it ECF. Okay, we do not call it ICF unless and until something is within the cell. We call it ICF, because this is a normal confusion students have. So this you have to be very clear about. What is inside the cell is called the intracellular fluid. What is outside the cell is extracellular fluid, which includes the fluid between the cells, which we call it interstitial fluid, and the fluid which is or the compartment which is the vascular compartment, that includes the plasma and the cellular component. Okay, so all that forms the ECF. So of the total body water, 2/3 of it constitutes the ICF and the remaining 1/3 is the ECF. Now of the ECF, again, 3/4 major component is by the interstitial fluid and remaining 1/4 of it forms the vascular component. Okay, so this is the part of the ECF. Vascular component is the part of the ECF. Is this clear to all of you?
Yes, ma'am.
So now, what are all the substances which cross the cell membrane? Basically, not all substances will be easily transported across the membrane. So there are certain like lipid-soluble substances, they are easily transported, whereas the water-soluble substances require sometimes the carrier proteins. Okay, so that's one of the function of the proteins which act as the carriers, and therefore it helps in the transport. Now, under the transport, we have direct, that is, I told you, all the lipid soluble will be easily transported, whereas the ions and the water soluble substances and also the water through the water aquaporins, transport is carrier mediated. Now, what's the difference between uniport, symport, and antiport? Uni is single. Okay, so it is unidirectional. Symport and antiport, it has got two binding sites. When it is symport, that means it is in the same direction. Then what is antiport?
Opposite against.
Yes, it is in the opposite direction. Are you all with me?
Yes,
Yes,
ma'am.
I'll just give you an idea today. Maybe next class, we will focus on exactly the clinical aspect of all of this. So now in the carrier mediated, now I told you some are carrier mediated. So in the carrier mediated, unlike in case of where you do not require a carrier, there are factors which will affect. One is competitive inhibition, which means if you have a molecule which is similar to that of the substance which is supposed to go and bind to the carrier protein, then they will compete with that. Are you following? So if the structure wise it is the same, then it will compete with the carrier protein. So this is what is called competitive inhibition. Next is we have a limited number of carrier proteins. So once the carrier proteins are all bound together, then beyond that there will not be any transport, which is called the saturation. Is that clear? So this is the difference between the transport where you do not involve the carrier protein and where you involve the carrier protein. Okay, so basically these protein channels, they are very selective in their transport and they are all gated. Now, if you remember what you studied in your action potential, because that you would have definitely studied, you say that there is a change in the potential and therefore there is the entry of ions. Yes or no?
Yes, ma'am.
Yes, right. So in the depolarization of the action potential, for example, a nerve action potential where you have the resting membrane potential of -70. Now you have a slight depolarization which goes up to -55 and you have a channel which opens. Which is that channel that opens during the depolarization?
Potassium channel.
No, it is a
No,
positive.
sodium.
Yes,
Sodium
it is.
channel.
Yes, right. It is sodium. Okay, so at that particular voltage, it is only the sodium channels which will open, and therefore there is depolarization. Now, as somebody, I do not know your names now, as somebody said, it was potassium. See, it is not potassium because that potential is not the potential for the opening of the potassium channels, which is why it will not open. So what do you understand now? What gated it is the voltage. Do you agree? Do you all agree? You all don't unmute and answer.
Yes, ma'am. We agree.
Okay, so now coming to the ligand, like how you study in the neuromuscular junction, what happens? What is the neurotransmitter in the neuromuscular junction?
Acetylcholine.
Very good, acetylcholine. Okay, what kind of receptor does it bind to?
Nicot.
Very good,
Nicotinic.
nicotinic acid. I'm glad you said nicotinic. Which is the other type of receptor?
Muscarinic.
Very good. Okay. So now what happens is when this ligand, which means the acetylcholine goes and binds to the acetylcholine receptor, there will be opening of the sodium channels. Okay, because the acetylcholine receptor itself acts as a channel, and it will open and it will allow the sodium to enter. Similarly, there are stretch receptors, which will, with the help of the stretch, there is opening of the channels. Some of the channels will open only in case of phosphorylation, when the phosphate gets added to it. So that is how the channels are gated. Any doubts?
No,
No,
ma'am.
ma'am.
Okay. So this is what I was telling you. So as soon as and when the receptor, I mean the ligand binds, you see that this opening voltage, there is a change in the voltage, it opens. When there is phosphorylation, it opens. And whenever there is a stretch, it opens. So these are the ways in which the gates will open. It is again the same thing. So you should remember that when you consider the concentration of sodium and potassium, where the concentration of sodium is more, is it in the ECF or ICF?
The ECF.
Very good. So what is more in the ICF?
Potassium.
Potassium. Yes, potassium is more in the ICF. Now, what will be the tendency of the sodium to move towards?
I don't understand your question exactly. What did
Yeah.
you ask?
So what I'm asking you is, as you said, sodium is more outside the cell, right?
Yeah.
Yeah, and that's correct. Now, what will be the tendency of the sodium to move towards?
It will move inside the
Yes,
towards
why
the
did you say it will move inside? Why do you think it will not stay outside?
because of the depolarization
No,
for the
I'm not talking about the depolarization. We are not talking about the action potential. In general, there will be tendency of the sodium to move inside. In what context?
because of the concentration gradient.
Yes, very good. Okay, so because there is higher concentration of sodium outside, it has the tendency to move inside. But the sodium cannot easily move inside. It's a water soluble substance, so it needs the carrier protein with that. Okay, now I'm just telling you to have an idea. Now you said potassium is more inside, so the tendency for the potassium to move outside is more. Okay, but if you go by the resting membrane potential, the permeability of the sodium and potassium, if you consider, the permeability of the sodium is much lesser than the potassium. See, if you go by the size of sodium and potassium, I'm little deviating. Now we have two ions, it is the sodium and potassium. Okay, if you go by the actual size, potassium is, anybody has an idea about the size wise which is bigger?
Potassium will be smaller.
Sorry, could you come again?
The potassium will be 1 second. The potassium will be bigger, I think. Yeah, potassium will be bigger.
Potassium will be bigger. Okay,
Yeah.
but actually sodium is smaller. Okay,
Yeah.
but what happens is there's something called water of hydration. It has a capacity to hold water. Okay, so when it holds water, what happens is uh, sodium, though it is smaller, by holding water, it becomes larger than the potassium, which means the permeability of the sodium becomes lesser than the permeability of potassium. Are you all following?
Yes, ma'am.
If you have not followed, I'll repeat once again. Anybody who has not followed?
Could you repeat? No.
Yes, yes. See, now if you go by the size, which is smaller, now you should tell me.
Sodium.
Yes, correct. Sodium is smaller. Now there's something called water of hydration. So when the water gets attached to the surface of the sodium, that's when you call it water of hydration, the size of the sodium becomes larger. So the permeability of the sodium will become lesser, whereas this water of hydration for potassium is lesser. So the comparatively now what happens is sodium will be larger than the potassium. Thus the permeability of the sodium will be what?
Lesser.
Yes. So it's difficult for the sodium to move as compared to potassium. Is that clear?
Yes, ma'am.
Yes, okay. So this is why this is important for you, because later when we talk about the resting membrane potential, we will always tell that it is because of the potassium and not because of the sodium, because the permeability of the membrane is more for potassium. Okay, these are all very basic, that is protein channels will conduct. I'll not waste time on this. Now, who studied this? This may be the question out of interest they can ask you. That was all the channels were studied through the patch clamp, and they received the Nobel Prize, that is Neher and Sackman. So there are different ways they made the patch, though that is not very important for you to know. As long as you know that who studied it, it should be fine. Now, yes, coming to the different types of transport, one is diffusion, or rather there is passive and active. Now, what's the basic difference between active and passive?
Active needs the energy.
Yes, whereas passive does not require energy. Okay, so the majorly passive transport is diffusion and osmosis, and also water flow, we call it also passive transport. Also filtration across the membrane is through passive transport, because it depends on the pressure. Active transport includes the primary and the secondary. Under secondary, we have two different, that is the co-transport and the counter transport. Now, diffusion, there are two, that is simple diffusion and facilitated. First of all, we have to understand what is diffusion. So here, what moves? You can take the help of the slide. What moves here? Molecules, right? So it's a molecules, but what molecules will move from its higher concentration to lower concentration? Remember, here I am talking about the solute, or the molecules which will move from its higher to the lower concentration. And particularly the lipid soluble substances will be easily diffused. Like oxygen, carbon dioxide, this happens in the lungs. Okay, diffusion happens in the lungs. Now, there is another type of transport which requires the carrier protein. And wherever there is a carrier protein, in that case, definitely we have the factors which will affect, and that is the saturation and the inhibition, competitive inhibition. And also it has to be very specific. So it will only specific carriers are there which can go and bind to. Are you all following? When I have a long silence, I get a doubt. Are you all following?
Yes, ma'am. Yes, ma'am.
Okay. Okay, so basically this is about the differences between all this. Maybe when you read also, you may not find it difficult. So in simple, no carrier. Here you have a carrier. Here you have, in facilitated, there is saturation, because you have a limited amount of carrier protein. In competitive inhibition, they have the structure which is similar. That is why there is a competition. And diffusion, because there is a carrier protein, it could be fast. Without the carrier protein, it is slow. And facilitated diffusion is very specific to the molecule. This is the same thing again. I'll skip that. What diffusion depends on is given by Fick's law, and he says that it is directly proportional to the surface area and indirectly proportional to the thickness and proportional to the difference in the concentration across the membrane. Okay, so that's about now. Depending on the permeability, this is what I was telling you. Water of hydration plays an important role in the permeability. Higher the temperature, better is the diffusion. Higher the concentration gradient or the electrical gradient, greater is the diffusibility. More the solubility, more faster is the diffusion. More the thickness, what happens to the diffusion?
It will reduce.
Yes, very good. Okay, so it has to travel more distance. That is why it is inversely proportional. More the size,
It will be reduced. Yeah.
reduces. Okay, good. More the surface area,
It will increase.
more the diffusion. Okay, good. Okay, so that's about the permeability, which I already told you. That's about the water of hydration. So you see, the size wise it's smaller, then you have the water of hydration, which makes it bigger and it becomes less permeable. Okay, whereas potassium is the other way. Now, what makes the saturation is nothing but what we call it Vmax, because of the limited amount of the carrier protein which is available for the diffusion. So we finished with the diffusion. So the next type of transport, that is osmosis. Now, how diffusion and osmosis is different? Anybody, you give me even a wrong answer, it's okay. I will get to know.
I mean, osmosis, we determine with the solvent, the movement through the solvent molecules.
Very good. Yes. So here it is the solvent molecules. There it is the solute. Okay. Or we simply in general we call it molecules. So here it is the solvent molecules or the water molecules, which moves from its what concentration?
From higher concentration to the
Moves from
lower.
higher concentration to lower concentration. Okay. So that is what through a semi-permeable membrane. I think from school we have been studying this. So from its higher concentration to its lower concentration. So here you have more of non-diffusible solutes. So water will move from here to here or here to here? Here to here?
From B to A.
Ah, very good. Okay. So wherever you have more of water, from there to the less of water, it moves. Okay. Yeah. Now you should know what is the osmotic pressure. So the pressure which prevents the osmosis is called osmotic pressure, and there are two terms which you have to know, that is osmolarity and osmolality. Okay, there's a spelling mistake here. Molality, L-I-T-Y, this is. So here when it is osmolarity, though it is R, you remember it is liter. So it's the amount or the concentration of particles per liter of water. Okay, whereas when you consider osmolality, it is concentration of particles per kg of water. Okay. Now, what is effective osmol? Now, I told you there are how many compartments? How many compartments are there?
Two ECF and ICF.
Yes, ECF and ICF. Okay. Now, you call something called effective osmol for a particular compartment. Now, what do we mean by effective osmol for a particular compartment is there is a substance which cannot cross the membrane from that compartment. Okay. Now, what is more in the ECF?
The sodium.
Yes. Okay. Now, tell me what could be the effective osmol for ECF?
Can you repeat the question?
Yeah. See, I told you now effective osmol for that for one compartment is a substance which cannot cross that membrane. Okay.
Yes.
Yeah. Now you consider the compartment to be ECF. Now you tell me, for an ECF, what could be the substance which is called the effective osmole for ECF? Did I get answer? Is my question clear? No, I don't think you're clear. Is it clear?
I'm sorry because I'm not understanding the question exactly.
Yeah.
So I cannot answer I cannot answer.
Yeah. Okay, see, now we have, basically, I don't think you all have understood what is effective osmole. The effective osmole for any compartment, we can say that if that compartment is not allowing one of the substance to pass through the another compartment. Okay, is this clear to you?
Yes, ma'am.
This point is clear to you. Okay.
Yes, ma'am. This point is clear.
Yeah. Now, what is more in the ECF? You tell me.
The sodium.
Okay, why it is more in the ECF? Why didn't it go to the ICF?
Because of the water of hydration, you said.
Yes. Which means it is not easily crossing the
Permeable.
membrane.
Yeah.
Which keeps the ECF compartment with more of sodium. Clear?
Yes. Yes, ma'am.
Now the effective osmole for the ECF is dash. You tell me the ion.
The sodium.
That is all it is. Is it clear now?
Yeah, now it's clear.
It's clear. Okay. Now coming to the vascular compartment. Is it the part of the ECF?
Yeah.
And
I'm not
this,
sure.
okay, you have to be. You
I'm not
answer
sure.
wrong. I will know you have not understood. That's why I ask questions. Okay, so vascular compartment, yes, it's a part of the ECF because so we said that ECF includes the interstitial
Plasma.
fluid. No, interstitial fluid and the vascular compartment. So the vascular compartment will include the plasma and the, what is there in the blood?
The RBCs and the other cells.
Cellular component. Yes, correct. Okay. Now see, I think you all are aware, plasma proteins cannot cross, right? It will not come out of the capillary. Will it? Unless you make a cut, blood will not ooze out. No, particularly plasma will not ooze out. Whereas the fluid can come out. How will the fluid come out of the capillary? What is that method called? Or the process called? No, clueless. You think of a capillary network, what happens there? You have the venous end of the capillary, arterial end of the capillary. Students, are you listening to me?
Yes, ma'am, but not know about this one.
You don't know about that. Okay, see, very simple. You have to remember that where does the exchange takes place in the vessel? Okay. So see, we have the large vessels and then we have the capillaries where there is exchange of all the nutrients. Is it not? From at the capillary level, we'll call it arterial end and the venous end. Correct? This you
Yes,
all
ma'am.
know, right? See, students, 1 minute. Okay, so we'll have a vessel like this and it will break up into, this is a schematic, okay? It will break into capillaries like this. Now this will be our arterial end. Now on this side there will be this. I think you should read about this little. Okay, this will be the venous end. So this whole thing forms the capillary network. Do you all agree with this?
Yes, ma'am.
No, yes, no.
Yes, ma'am.
Okay. Oh, sorry, I erased that. Okay, so you understood this side is the arterial end, this side is the venous end, and the exchange takes place here. Okay, now the fluid from here will move out, and the fluid from here will move in. Okay, that is how the tendency is. But if there is no balance between these two, then you can have the fluid in the interstitium. That is what is called edema. Have you heard about edema?
Yes, ma'am.
What is edema?
When the fluids retains in the in the external compartment. Yeah.
In the interstitial space. Okay, so between the cells, wherever you have the space, if there is fluid there, that is what fluid gets accumulated. That is when you call it edema. Now, what is the cause for the edema is the difference between the filtration and the absorption. Okay, so if the filtration is more and the absorption is less, automatically fluid will remain here. Okay, and what is the reason for the more of filtration and less of absorption is particularly the plasma proteins. Okay, why I came to this is you should understand that if this is our vascular compartment, okay, we will have the plasma proteins here. Okay, and because of this plasma proteins, it will exert the pressure, and that pressure is called the colloid osmotic pressure. Okay, it's called the, what is that pressure called?
Colloid osmotic pressure.
Yes, it's called the colloid osmotic pressure. So in case you have less amount of plasma proteins, what will happen to the colloid osmotic pressure?
They'll decrease.
Very good. Okay, so that decreases. So if the colloid osmotic pressure decreases, and there is another pressure which is exerted by the water, okay, and which we call it hydrostatic pressure. Now, what determines the filtration is if the hydrostatic pressure is higher than the colloid osmotic pressure, there will be more of filtration. Okay, I'll not repeat this one again. I'll just check if you know. What did I say?
If the hydrostatic pressure is more and if the colloid osmotic pressure is less, then there'll be more filtration.
Very good. Okay, that's good. Okay, so there is more filtration. But if the what has been filtered, if it is not absorbed, then you have accumulation here. So suppose I have a condition where the colloid osmotic pressure is low. So what do you think should happen?
There'll be more filtration.
Why did you say so?
Because for osmotic pressure, we need proteins, ma'am. There's less proteins, so it will favor filtration.
Yes. So what holds the water is actually the colloid osmotic pressure, and which is being exerted by the plasma proteins. The moment the plasma protein reduces, the colloid osmotic pressure will reduce. So the difference between the hydrostatic pressure and the colloid osmotic pressure will increase, which will increase the filtration. Okay, that is the responsible for edema. Is that clear? Okay, now coming back to plasma proteins. So why I told you this is this plasma proteins usually will not be filtered except in diseases. Okay, which means the effective osmole for the vascular compartment is, why you all are not answering?
You mean like increased?
Ma'am, what's your question here?
You didn't get my question?
Yeah, ma'am. I mean, what's your question here exactly?
My question is again like my previous question. I'm asking you, what is the effective osmole for the vascular compartment? Effective
Plasma proteins.
Very good. You understood now why plasma proteins for the vascular compartment? This is the reason. It will not allow this. Got it? Did everybody follow? Yes or no?
Yes, ma'am.
Okay, okay. Okay, a little about the active transport. I'll not take much time here. I just want to give an understanding of the active transport to you all. So it requires energy, and it is against the gradient. It has to require a carrier protein. Again, depending on what is the kind of transport, most common one, what we talk about, which is responsible for the maintenance of the resting membrane potential. That is the sodium potassium pump. I think all of you know about this. You all know, I thought. Okay, anyways, we have three. See, now, where sodium is more?
Outside, ma'am.
Outside. Good. So, in active transport, where the sodium has to move?
Inside.
Sodium has to move inside. Why? If you say outside, you should tell me why. Sorry, I had to go out. Yes, tell me. You all said, if you all said inside is, it has to move inside. Why sodium will move inside? Students, am I audible?
Because of concentration, the concentration gradient, yeah.
Huh. Which means when it is more outside, it has to move inside, according to you, correct?
Yes, ma'am.
So do I need energy to move in that direction? Always make mistakes, but learn correctly.
Yes.
Huh? Do I need energy to go downhill?
No, ma'am.
No. So what example am I asking you all? I'm asking you about active transport. So in which direction the sodium should move?
Uphill transport.
Come again, please. Please answer it. I couldn't hear you. Sorry.
Ma'am, while doing uphill transport only, we require ATP, ma'am.
Correct. Only for the uphill we require ATP. See, basically it is like you already have enough of pocket money. They're still giving you more. So you don't know how to spend. Okay. So here what happens is you already have enough of sodium outside the cell. Okay. So you're further pumping the sodium. It's already there. So there is no gradient. Okay. There is no gradient across the membrane for sodium to move out. So it is against the gradient for which we require energy. So in an active transport, unlike in case of passive transport, the sodium will move from outside to inside. In active transport, sodium will move from inside to out. Okay. Now you all tell me what happens to potassium. Don't worry if you give wrong answers. You don't have to feel bad at all. But you all give a try. I will also learn from with you all. It's okay.
Potassium will move from outside to inside during the uphill thing.
Very good. That means you understood. So potassium will move from outside to inside. Although potassium is more inside, we are still pumping potassium from outside to inside. Okay, for which we require energy. So there is no gradient here. That much is what you have to understand. Here you are against the gradient. In passive, you are along the gradient. Okay. Yeah, in this sodium potassium pump, what happens is it's not equal the amount of ions moving out and moving in. So 3 sodium will be pumped out and 2 potassium will get in, which means you'll give 3 chocolates to somebody and you get 2 chocolates back. Are you at loss or gain?
will be at loss.
You're at loss. Okay, your
Yeah.
loss of how much?
1 sodium.
Minus
Oh,
1.
sorry.
Yeah, yeah. Right? Minus 1.
Yeah.
Or 1. Okay, if you go by that, we say it 1. But basically, minus of 1, right? Which means the membrane becomes more negative. So that's why this sodium potassium pump is called the electrogenic pump. It's called the electrogenic pump and it's responsible for the resting membrane potential. Is this clear to all of you?
Yes, ma'am.
Okay. Is it clear to all of you?
Yes, ma'am.
It's okay. Huh? Quickly, I'll finish the secondary and I'll not take more. That's all I'll cover for today. Okay, now, so primary transport will derive energy with the breakdown of ATP. So we have ATPase here and there's a carrier protein and the transport is always against the gradient. This is in opposite direction, so it is antipode. Similarly, we have pumps in the hydrogen pump in the gastric glands and the renal tubules, calcium pump with the sarcoplasmic reticulum. Now, secondary active transport is different from the primary active transport in a way that it derives the energy from the primary active transport. Okay, and so the direction of the substance could be in the same or in the opposite direction. Okay, now with this example, I mean secondary active transport, having known that it derives the energy from the primary transport, you have to tell me now that in active transport, now where is more of sodium?
Outside.
Ah, correct. Now what is the tendency of the sodium to move? When I say tendency, it should not require energy.
To move inside.
Very good. That means inside because it's already more. Now you have the gradient from inside, outside to inside. Okay. So all the, see, if you see here, what is common for us is sodium. Correct? Huh? Which means sodium once gets attached to the carrier protein from the outside. Along with that, there will be some other substance and both of it can enter inside. Even in counter transport, sodium will get attached to the outside and get transported inside, and in exchange there could be some other ion which moves outside. That is when you call it counter transport. Am I clear?
Yes, ma'am.
Okay. So how you derive the energy? See, by the pumping of the initial primary transport, you are creating more of sodium outside, which is why we call the secondary active transport is deriving the energy from the primary active transport. Okay. So co-transport, just remember this because you'll have question which will be followed later. Co-transport, glucose, amino acid will combine with sodium. So you can see the carrier protein and how they'll enter inside. So this is inside and this is outside, ECF. Okay. So you can see this is in the renal tubules. We have glucose and sodium and amino acid. So glucose and amino acid has been absorbed through co-transport. Now counter transport is sodium will enter inside the cell and hydrogen has been secreted into the lumen. Okay, so that's counter transport. I'll not talk about intercellular. I just want you all to answer this question. The primary force moving water molecules from the blood plasma to the interstitium is plasma I'm talking about, and it is water molecules which is moving, and it is from the plasma to the interstitium.
Is the infiltration?
Filtration, very good. So that's what I told you, no? Whenever we have the proteins, it will prevent. Proteins that are secreted by the cells, this I didn't cover for you all. Anyways, they are found in the vesicles and the secretory granules. The form of transport that requires expenditure of energy.
Active transport.
Good. Okay, the movement of substance along the concentration gradient with the help of carrier protein.
Facilitated diffusion.
Yes, because carrier protein. Transport of sodium and glucose is an example of
Symport.
symport. Okay, good. Transport of sodium and hydrogen is an example of.
Antiport.
Okay, good. Okay, that's all for today.